Thank you for the introduction. My name is Connor Glossner from Purdue University. I'm presenting FUZZUER, enabling fuzzing of UEFI interfaces on EDK-2. And to start with some motivation, in recent years, there's a lot of publicity about logo fail. 2023, binarily discovered a way to get arbitrary code execution during the boot process. You get bootkits, rootkits, and these were all common memory corruption bugs. They got 24 CVEs across 11 different vendors. And this was in UEFI. And kind of, so to emphasize the importance, it was just pretty much required you to overload the image from the OS. Didn't need any special privileges. So now you might be asking, what is UEFI? UEFI is the firmware that we were testing across, and it is a modular firmware. It's the Unified Extensible Firmware Interface, and it just defines a specification on how the firmware should interact. That way, vendors themselves can independently develop drivers for their hardware. That way, they don't need to communicate. It adds more security features like secure boot, and it also enabled easier user-friendly interfaces. And so, to give you a detailed overview of UEFI, that way you can kind of understand what we're looking at, is there's 4 phases to the boot process of UEFI, and we are specifically looking at the driver execution environment, the Dixie phase, and there's, in that phase is where all the user interactions, interfaces that get exposed can be directly accessed. So there are other tools that look at UEFI specifically, and so in red up at the top, you can see there's RSFuzzer, ChipSec, and Excite. Those are 3 different tools that look at a subset of drivers within the firmware. Those drivers can be accessed from the operating system side. And then there's HBFA, which is what we compare against in our evaluation, which looks at the closest to what we look at. It was all the drivers on the system. We don't look at the subset, we look at drivers that can be accessed from the shell itself during the boot process. HBFA specifically stubs out drivers and creates harnesses on top of them. And then finally, there was SymFuzzer, which just injects the data directly into memory and allows for random data types. It's just a naive fuzzer, but it focuses on the entire system and can pause and create snapshots at the boot process. That tool, though, was closed source, so we couldn't compare against that one. And so to kind of talk about the challenges within UEFI itself, because it's such an arbitrary, it just defines interfaces. It's trying to be very general to allow communications and independent drivers to communicate with each other in a weird way. There's a lot of types that aren't defined. They're left as void, generic types. So it creates a challenge when you're trying to generate input to fuzz those functions. So that was one challenge, for example, like in this image, getInfo takes in a void type, but that void type can be any type of packet. In this case, it could be an MTFTP packet, or it could be a packet for a different type of functionality, like a TFTP. And then the other challenge we ran into was generating state-dependent data. How can we pretty much get the state of a boot process when it can be asynchronous? There's interrupts, there's random kind of functions that get called, data can come in various different ways. And so how can we create structured data to then fuzz the system? And so this is where our solution came in. And our tool, FUZZUER, it has 3 components. There's FIRNESS, which is our static analysis assisted harness generation. And that's where we do templated harness generation. I'll explain most of that here. And then we have sanitation. We had to add support for ASAN within this, within the low-level environment. And then finally, the FUZZUER itself. So let's talk about FIRNESS. There's 3 main parts of FIRNESS to generate these harnesses to have structured input. And since we're generating source level harnesses in C, that way it can be modified and changed because the specification itself is generic across different implementations. So vendors themselves can have different internal code. And we wanted this tool to be as generic as possible, even though we tested it on the open source EDK-2 that was available. But the first step was our reaching definition analysis. So here we focused on collecting any constants. So the input was only function that we wanted to harness, the target functions. And so we looked at all the arguments that they took. We collected any assignments that happened any assignment that happened through another external function call, any assignments that happened through constants. We collected all of that information, and we created a map across all of the functions in the entire code base. And so, for example, for what I showed earlier, you can see the code, and then on the right-hand side, you should be able to see the output that we'd get from the map. And we create it in a stack order. That way, when we parse the data later, we can follow the correct order of assignments. And so the last assignment that happened was, in this example, packet. The set packets, the assignment was happening in the direction was outward because it was getting used. But previously, like get info, the assignment happens because that's where packet is actually getting set to a variable. And so then second, that input that I just showed you is going to be passed into our call site analysis. And here's where we're going to parse all those call sites for the functions, the target functions of interest, and any of those generator functions. So any of those functions that do assignments to variables or arguments of interest. And so we're going to go through all of those and treat them as the same. And we'll collect information that will be used in our harness. And since we're doing source level, we had to do this across the AST rather than the IR level. That way we can get actual type information so it doesn't get broken down to the simple structured information that it would be in the IR. And so, for example, showing the same example before, set packets here, we have your arguments. There's 12 arguments or 13 arguments that go into set packets. I'm only showing you one of them, but it used that assignment that was shown before where you have the argument direction, you'll have the argument type, the assignment that happens, so it's a generator function that's getting used in this case, get info, and it'll do this for across all of these arguments using the reaching definition map that I showed previously. And the key thing here is there's also potential values, so depending on branching and paths that were taken, there might be multiple assignments that could be possible for that instance of the argument. And this will do every call site and every instance of set packets across the whole code base or any other target function. And then finally, we pass all this information into our templated harness generation, which we used to, which we would analyze that information and get the actual argument type. So if there was voids, we do frequency analysis on the void types to determine what the most probable assignment it should be for void. There were other methods we did based off of heuristics inside this code base. But then we would also do argument value, which were constants that we collected. And then finally, we would perform that same analysis on generator functions in a recursive way. That way we could also have structured generator input. That way it wasn't a chance that we were going to cause the whole system to crash for no reason. And so an example harness is, it looks very similar to the source code I was showing you before, but with some random input. So you have your random up the top, that's a scalar value that it's just reading in some random data from the input stream. And then eventually down below, you can see that we have structured input that's getting read in, get info is getting used, which is that generator function, which is going to create stateful data that will then eventually get passed into set packets, which was what we were trying to, the function we were targeting. And then finally, the last two components of our FUZZUER was the sanitizer instrumentation and the fuzzer itself. So the sanitizer instrumentation, we designed ASAN runtime libraries for EDK-2, and we were able to inject those in and run ASAN instrumentation on top of the code base on a low level, where the main challenges were the memory management on the physical layer, physical level. And then finally, there was the open source fuzzer we used by Intel, the targeted software fuzzer for CIMIX. We added some minor modifications to it to get better coverage information. And then, so after that, this would be our system view. Now that we have a harness, where would it run on top of? Since UEFI is less discovered, it actually has a shell that's available that you can run applications from, similar to the Linux kernel. And so we ran on top of that. You can see the blue is our FUZZUER app. And it's running on top of the UEFI shell, where we run inside that simulated environment, and we have libafl as the fuzzer, the underlying fuzzer for it, and that's where we're able to call all the interfaces of interest. And so this led us to try to address a couple questions. We had 4 questions we were trying to cover. How effective were we at collecting, how effective was our static analysis at collecting and analyzing these void stars, or the void types, generic types? In general, how was it at collecting all the functions of interest and generator functions? And we did this manually by comparing what we collected to what was actually generated automatically. And the two main questions that I will show you results for was how effective was the fuzzing itself, its bug finding ability, its code coverage, and how well did it perform against our best effort evaluation with HBFA, which is a host-based firmware analyzer, which is the stubs, which runs on stubs and manually written harnesses. And so to look at the bug finding ability, we were able to find 20 new bugs and reported them all. About half of them have been confirmed, and the rest have just still been reported and unresponsive. But you can see across the bottom, you can see how well it performs with different variations of our fuzzer. And with the random fuzzer, which doesn't do any points to analysis, with no type information, no generator function, it performs the worst. And the without points to it also has the similar performance. And we were able to discover that's because sometimes there's no call site information, so the analysis, we needed points to information to actually track back to the function definitions in the system table. And then overall, though, we were able to get good coverage, the best performance with more of our analysis techniques enabled. And overall coverage had a similar effect. With all of our analysis techniques enabled, we were able to achieve greater coverage because we were able to get the complex data types and the stateful information and achieve greater code depth compared to some of the other ones where the red is the random, and you can see that's pretty much towards the bottom in most cases because it wasn't able to reach deeper in the code with blocking statements. And then overall, our comparison with HBFA, we were able to have greater code coverage across every test. We had 3 bugs that we were able to find that they were not able to find when we compared against them. And we also had our harnesses had a greater size in general, which just emphasized, and they were not very complex, emphasizing the need to have some more of an automated system in place rather than manually writing them with system expertise. And so, in conclusion, we proposed FUZZUER, which is our coverage-guided fuzzing framework for UEFI functions, on top of EDK-2, which is the Tiano core implementation. We also proposed FIRNESS, which combines static analysis and templated harness generation to craft source-level harnesses for UEFI, and we demonstrated its effectiveness with its comparative evaluation. We were able to find 20 new bugs within UEFI. And our code is open source if you want to build on top of it or work with it. Thank you.
All right, thanks for your presentation. Very interesting. Anyone has a question? I invite to stand up. Yeah, okay. I wanted to focus a little bit on the code generation part, right? You say that your approach is based on static analysis. From my end, I didn't understand whether your analysis is focused on the, let me say then we explain better, on the consumer part or on the UEFI code. So there is the UEFI code, right? Mm-hmm. And some other part that is used interacting with the interface. What of these two parts are you analyzing?
Both.
Both, okay.
Yeah. So we cover all use cases from any applications that it might be called from and any internal function calls that are happening inside the source code.
Okay, so is it, okay, thanks. That was not really clear. Okay, thanks. Did you write your own analysis or you are based on other tools?
I wrote my own analysis and we drew inspiration from other Linux kernel level harness generation tools.
Yeah, but I mean, you work, let's say, at, usually for static analysis, you work at LLVM IR level.
Oh, yeah, so I wrote my own analysis because all the analyses take place on the AST.
Oh, all right,
yeah.
Okay. Yeah, then when you perform the fuzzing, it's not clear to me if the UEFI code is emulated or run on the physical machine. That maybe you said in the slide, but I missed that.
Yeah, it's emulated. So Symix was the emulator we used. It's a higher fidelity simulator compared to Qemu. And so we were able to get more hardware features enabled when we were fuzzing it.
Okay, thanks. And last question that I have is about a more broad spectrum of your approach, because to me it seems like very oriented about generating the harness, right? And I see a plethora of works about harness generation work. So I wonder if this approach can be ideally be applied to other scenarios, and if you can talk about that a little bit.
Yeah, no, that's a great point. It can be. So we use UEFI specific heuristics inside some of the analyses, but if you modify, since the source code's available with our passes, or Clang passes, those can be applied to other code bases like a Linux kernel or any other external library in any space, as long as there's, you remove some of those heuristics and add some other ones, but everything else should still be usable.
All right, thanks. And you should go, or well, maybe
just a quick question. I'm curious, what is the type of heuristics you're mentioning here? UEFI specific heuristics. Do you have an example of those, or?
I don't know if I can go back. Oh, I can. For example, let's see. In the argument direction, they have qualifiers in EDK-2 that are part of the specification, which define what direction the argument is going in, whether it's going to be going in or out of the function call. So that was one of the specific heuristics we used to determine the direction and if an assignment was happening with a generator function, rather than needing to do a more advanced analysis to actually determine if an assignment was happening in an external function call. It kind of gave it to us by looking at the function definition. And there were some instances where it might go in and out, and so we had an additional analysis to handle those cases, along with like void types. We didn't want to resolve all the way down to the simplest type, because sometimes like there are EFI events, which is like if an interrupt happens in the system, we didn't want to necessarily say it was a void. It's actually an event that's specific. So those were unique scenarios that we had to take.
And maybe just a quick follow-up question. Oh, sorry, I'll take it offline.
Sorry to interrupt you, but we are running out of time, and I invite you to contact offline after the presentation. Thanks again for your interact, and a round of applause for coming.